Hello and welcome back to the final part of my ECE5000 electrical engineering design project. I am Noah Bailey. I'm a Term 5 electrical student at Memorial University of Newfoundland, and this, as I mentioned, is my project for the ECE5000 course. Within this course, every student picks a project from a list. Each project is individually done and they are distinct from one another. And at the beginning, we are all provided with a kit that can help us, as well as access to all of the components, parts, tools, and help that we may need to realize our projects. My personal project is a 120 volt AC load measurement device. This device measures the voltage and current, and from these values calculates the power and energy of a load. And it has two outputs for these calculations and measurements, and that is namely a liquid crystal display and an SD card. The entire project is based on Arduino, and so for this project I used an Arduino Uno R3. Let's go ahead and jump into how this project began and where it went. So, setting out my objectives was something that I needed to do before I could really get into the work of designing and implementing this, and so I started out by listing things that I wanted and that were required for this project. So firstly, it was required to measure 120 volts AC, but I thought, why not go higher? Some places in the world don't use 120 volts AC for their wall outlets. They use higher, like 220 or 240. So that was one objective there, is to get as high of a voltage as I can that I can safely measure for this design. I also want to measure as high of a current as I can because some devices draw a large current. I don't want them to be excluded from use for this design because of their large current, such as some toasters may have quite high wattages and draw a large current, or other loads like that. I don't want it to be restricted to just small use cases. I want it to be pretty universal. So the goal was to get current measurement as high as possible. I want the design to be safe. I wanted it to be easy to use and easy to set up. So this means solid connections, insulation, easy access to what needs to be accessed, such as the probes that need to be connected across a load, or the SD card that needs to be removed, or the safe eject button for the SD card even. I wanted these to be easily accessible and safely accessible because I don't want to hurt myself, hurt someone else, or hurt any of the design or components. I also, as I mentioned, want it to be pretty universal. I want it to be able to measure almost any load in reason, so that was something that I had to consider when I was designing my circuit. Alright, so here is a look at the circuit diagram that I created for my project. So firstly, you'll see right here, this is the load that is to be measured. So I put in a bulb, for example, and an AC source. So this would be a 120 volt AC system. And this is connected directly to my two sensors, the ZMPT101B voltage sensor and the ACS712 current sensor. Now, the ZMPT101B has obviously a VCC, which is 5 volts coming from the Arduino. It is grounded. It has two grounds, but only one of them is actually used in the design. And it has an out to analog port A0. It also has two ins, which of course need to be measured in parallel, so they go across the bulb. Then the ACS712 similarly has a 5 volt VCC power, and it has output to A1 of the Arduino, and it has a ground, but then it needs to be measured in series, so the current through this circuit actually goes through the system and back out as such. So those sensors are pictured here. Then I'm going to skip over the Arduino itself for now, and we'll go up to the SD card module. Now the SD card module has 6 pins. We have a chip select, a clock, master out, slave in, master in, slave out, a VCC, and a ground. The chip select, SCK, MOSI, and MISO go to various digital pins of the Arduino. Alright, let's jump over into the LCD. So V0 is actually a potentiometer, which controls the contrast of the screen. The potentiometer goes to the 5 volt rail as well as to ground, and then to this pin. The D4 goes to D8, D6 goes to D6, so on and so forth, and then E goes to D3. We can also note that RS goes to D2 here. So the LCD is configured so that the potentiometer adjusts the contrast of the screen, and the rest is pretty self-explanatory. The A is a drop-down resistor of 220 ohms, which then goes to the 5 volts. Down here we have our LED, which is an output from the Arduino, so it is just connected to a digital pin. Similarly, we have a button, which is an input. Now the button, when it is pressed, will activate this system that ignites this LED. The power supply for the Arduino would be up here, and that is powered by a power barrel, which is plugged into the wall. And then the 5-volt rail comes out and powers all of the other components. Both grounds are grounded here. The only two analog ports used are A0 and A1. And then essentially every single digital port is used on the board. Now, it is worth mentioning that this circuit diagram only features the Arduino Uno, but in the actual implementation, there is an Arduino shield attached to the top of the Uno, but this is the basics of the circuit diagram for my design. This is a nice view of the board that I used as the center of this project. Now, I said that it was based on Arduino, but I actually made use of an Elegoo Uno R3, which is essentially identical to an Arduino Uno R3. We can see all of the different pins here. We see the power barrel versus the laptop connection via USB. On the side, we have our 5 volts and our grounds, as well as our analog ins, all of our power connections. On the top, we see the microcontroller, and then on the other side, we have all of our digital pins, which includes PWM. Here we have a nice look at the ZMPT101B voltage transformer. We have the IC itself, the large blue box. You will also notice the smaller of the two blue rectangles with a small flathead screwdriver spot on the top. This is an onboard potentiometer that can be used to calibrate the device. Here we have a look at the ACS712. This is the -20 amp version. This current sensor uses the Hall effect to determine the current. Here is a quick peek at the SD card module. This is used in my design for the communications back and forth to the SD card so that we can create a text file which can be viewed on other devices. Here is a view of the LCD screen that was used in my project. Now this has a pretty large pinout. Within the circuit diagram and the block diagram, we can see a clear wiring diagram for this 16-pin device. This is where my values are primarily displayed, as well as the SD card, which we have seen. Here is just a brief look at the empty housing, as in none of the components are inside of it. We can see the voltage label on the top and the current label on the top. We can see the inside of the housing, which has some braces to hold my components in place. And we have some rubber legs on the bottom here, as well as a hole for the power supply to the unit, whether it be from a computer or from the wall. Here is the Arduino code that is currently installed on the device. And if you have seen the previous parts, this is a code that you have definitely seen before. So I'm going to go through it once more, and I'm going to highlight some of the things that changed over time. So as I mentioned, the initial setup is before the void setup and before the void loop, where I include any libraries that I need. I set up the file for the SD card. I set up my button and LED, which are for the safe eject feature. I set up the LCD, and I set up a bunch of floats, which are going to be used for getting my measurements. Now, initially, I did not have the current sample sum or the current mean set up or the current sample read set up in this way, but over time, the code changed so that the current would get a more stable value and thus the power reading would be more stable, so those were added in. Here we have the setup for the current measurement, which involves the sensitivity of the device. Then I just set up some floats for the power energy and total energy. Then we have the void setup, which is where the LCD is initialized, the button is set as an input, the LED is set as an output, the button state is red, and the serial logger is begun, and then the initialize SD is called, which we will see at the bottom. Here we have the main loop. Now this is where the real work happens. The button state is read at the beginning of each loop, and then we begin taking samples every 0.2 milliseconds. Now these samples we take for the voltage and for the current. So for both sensors, there is a sample taken. As I mentioned before, the current wasn't measured in this way initially. It was measured down here. This step is simply taken and condensed and placed into this. So instead of taking one measurement at display time, I take that same measurement every single sample time and do the same process as with the voltages, where I take a reading every 0.2 milliseconds, sum these up, and then divide them by the total sample count. Then once we have a voltage sample count of 1,000, we calculate the current mean and the voltage mean, which is, as I said, the sample sums divided by the sample counts. And then we adjust the values so that we get an RMS voltage, and we have some sensitivities so that if any phantom currents or voltages are read, they are not displayed. And then we have our prints. Now, I do print to the serial monitor, but in the final design, it is not connected to a computer, so this isn't doing all that much, but it doesn't hurt. Then we have the LCD statements here, which displays the values on the LCD. Then we have the statements that write to the SD card file. And we have a reset at the bottom so that the sample sums and sample counts are reset and the loop re-begins. If the button state goes high, as in the button is pressed, eject SD is called, which we will see down below. Now those two functions, initialize SD and eject SD, are seen down here in the secure digital initialization and safe eject section. First, we have the void eject SD function, which we saw right here. And this just closes the file and writes the LED high and then writes it low again. We know that while this LED is lit up, it is safe to eject the SD card because the file is closed. And if the SD is not attached, we will get initialization failed, or if it's not formatted properly, we will get initialization failed, or if it is okay, we'll get initialization done, and then we will see that it writes to the data.txt file, and if not, it prints that there is an error opening it. So when we take a look at the SD card file, we will see this testing123 at the top, and then followed by all of our values here, which are printed from our measurements. But this is a final look at the final working code. It has definitely seen some tweaks, including the sensitivities, such as this one here, the 0.00. You can change that up or down to make the currents change. QOV you can change. As well as on the actual physical devices, there's potentiometers and settings to change to make them more or less sensitive and to adjust those values. So these were constantly changing throughout, as well as the sensitivities and whatnot to get an accurate reading. But it is at the point now where for my specific current and voltage sensor, they are very accurate. We'll take a look at the housing here, but I think it looks pretty nice. It's a wooden box. It has 4 support legs. There's slots on the top for the LCD as well as for the 4 probes. I was initially considering mounting the SD card with a slot on the front, but the SD card module in itself is very hard to access, so I decided to leave it loose out of the back so that you can access it pretty easily. And overall, the design fits very nicely in the box, and of course with this, the components are shielded and protected within this housing, so they are less likely to be damaged. But also on top of this, I needed to make sure that there was no shorts that were going to happen, so I insulated everything that was in there that could potentially short so that it's safer and I don't accidentally bust anything when I'm testing it. So firstly, let's do a little recap of the project, how it started, and where we are now. So I started out just by thinking of my project and trying to get a basic idea of what I needed to do and what I wanted to do with this project before I did anything. Then I started to draw up some circuit diagrams, some block diagrams, list out my objectives for the project, and then I started to simulate it with Tinkercad and ModelSim and other online programs so that I had an idea of what I was first going to implement. Then I did my first implementation on a large breadboard where I had tons of space and I could see all of the components individually spread out, and I could make sure that they were working and they were wired up correctly. Then I jumped into the testing phase where I introduced an Arduino shield with some soldered components. I cleaned up the design, I put it in the housing, I insulated some parts, I made sure it was safe and working and looked appealing. Throughout all of this, I was constantly updating my circuit, I was constantly updating my code, I was constantly making tweaks and calibrations to ensure that my values being measured and displayed were as accurate as possible, checking these oftentimes with a multimeter that I had myself and comparing these values to what I was obtaining from my design. So in terms of some specifications for my design, the housing and the overall thus design is around 7 inches by 4 inches, maybe a little bit less on both of those dimensions, ever so slightly. It is supplied by 9 volts DC. It will never consume more than this power, so this is an adequate power supply. It can support at maximum 20 amps of current and 250 volts RMS AC. So these are pretty high values that you often won't go over. And so this is a design that is pretty suitable for any at least at-home applications or low voltage applications. But each of these components has its own specifications that must have been considered when designing the specifications for my overall creation. Now, another thing that I would like to consider in terms of specifications is the accuracy of the design. Now, obviously, if you were to take this design and create it on your own with your own components and your own board, you would have to make tons of tweaks and changes to not only the code, but to the sensors themselves, since they took a lot of calibration and a lot of tweaking, and no two items are identical. So if you have a ZMPT101B voltage transformer, it's not going to be the same as mine. So the calibrations are going to be ever so slightly different on these two devices, but mine is calibrated to be quite accurate, at least when compared to my multimeter at home, and so I think that it has a very high degree of accuracy. It's pretty easy to set up and use. The box is labeled so that you know which 2 probes are for the voltage and which 2 probes are for the current, and then the rest is essentially just plug in the Arduino and make sure that the SD card is in the SD card module. And then when you want to eject the SD card, make sure you push the button for safe eject. Other than that, there's not much that can go wrong with this design. It's pretty solidly connected in there, and it's pretty much just plug and play. Now, before we jump into the demo, I just wanted to go over a little bit of what this demo will actually show you. So for my demo, I'm going to set up my design, and I have 3 different loads to test. These are a 40 watt, a 60 watt, and a 100 watt bulb. I'm going to interchange these, and we'll take a look at the values that are displayed on the LCD and make sure that they line up with what are expected. And then after that, I'm going to eject the SD card, move it over to my computer, we'll open up that file, and we'll see if that matches what the LCD was displaying. So firstly, as you can see here, the smallest of the 3 bulbs is a 40 watt. This will be the first test case that we go for on the demonstration. And then secondly, we have a 60 watt bulb. This is going to be the second demonstration case for the upcoming segment. And then finally, we have a 100 watt bulb. It may be a little bit hard to read there, but this 100 watt bulb is going to be the biggest, brightest, and final test for my design. Let's go ahead and jump into the demonstration. So here we are jumping into the demonstration, and the first thing that you'll notice is that I have a 40 watt bulb here in my hand, which was just attached to the design. This is the smallest bulb that I'm going to be testing, and also the first bulb that I'm going to be testing. So I'll put that back in there. On top of this, you'll notice I have a 60 watt bulb, as well as a standard 120 volt 100 watt bulb. Now the printing on this one is a little faded, so it's sort of hard to see, but it is a 100 watt bulb. These are going to be the other 2 tests in this demonstration. So now the first step that I'm going to do here is to just plug in my design. There's the 120 volt to 9 volt adapter that goes into the wall. I'm using a separate plug than the one that is running my load just for safety. Now we will observe the screen, and we will see that it is reading all zeros. This makes sense because the power bar is turned off and the light is thus off. Now I will go ahead and set the camera back up here, and I will come over and turn on the design. We'll see the bulb lights up. Woohoo! Now, if we were to check the values that are being measured by this, once again, this is the smallest bulb, the 40 watt. We should expect somewhere around 40 watts. We will see 121 volts, 0.33 amps, and just under 40 watts at 39.8, 39.9 watts, which is pretty accurate. I'm just highlighting here the connections for the current and voltage, which are in series and parallel, respectively. Next up, I will go ahead and switch the bulb. Now the bulb does get hot very quickly, so I have to be careful when switching the bulb, making sure it is not hot. And here I go to switch the bulb. Next up, we will do the 60 watt bulb. So this bulb is a little bit more powerful, a little bit brighter. I once again have the power bar turned off while I'm doing this. We'll see that currently the device is reading all zeros again, which will be noticed later on in the SD card section. But here we go, we turn it back on. We see the bulb is on, and let's go ahead and check the values. We should expect a value around 60 watts. We see that it is 58.6 watts, which is about half an amp, which is accurate as to what it should be. It is with a high degree of accuracy that this is being measured. Now we will go ahead and switch the setup once again to the final bulb, which is the 100 watt, the brightest and most powerful bulb. Once again, the bulb is hot, so while I switch it here, I just have to be careful. I have everything turned off for safety. Here is the 100 watt bulb. Once again, it is a bit faded, but it's hard to see. Here we go. I will screw this final bulb in for the demonstration. I will make sure all the connections are good and turn it on. And wow, that is a bright bulb. I will grab the camera once again here and come over. We should expect a 100 watt reading. We see that it is 101.7, 100.6 at around 0.83, 0.84 amps. Now this is quite accurate as well. Now once here I'm just highlighting that the potentiometer will change these values as is expected, but the potentiometer is not the main focus of this demonstration. Next up, the last step of this demonstration is to safely eject the SD card and then remove it, and we will jump into that section. So here I am turning off the bulb, and I will reach into the back. I will press the safe eject button, which is just located in the back of the design. You can see it lights up sort of a bluish purple, and then that means the SD card is safe to eject. I'll pop out the micro SD, and now I will move that over to the computer where we will take a look at the files that is produced. Here I'm just deconstructing the setup, unplugging everything so that it is safe and nothing can be damaged. And here I will jump into the SD card. So here we are on my desktop, and if I go ahead and pull up my file explorer, we will see that I have a connected drive, CAM 128GB. This is the micro SD that was being used for the test. You'll see I have two files here. SD test is a text document where I was first initializing the SD card and testing it to make sure it worked. And then the second, data, is the one that was just produced from the demonstration. So we'll go ahead and open this one, and we'll take a look. So we started out with the testing 123. This is the SD card, making sure that it can write to the file correctly. Then we'll see a bunch of values that are just read as zeros. This is because nothing was turned on. And then we'll see this moment here where the first bulb was turned on. For a second it reads 30 volts, but then as it gets time to adjust, 120.94, 0.33 amps, and the power reading was 40 watts. We'll see that the energy continues to increase every step because energy is a measure of power times time. Then eventually we will see that this goes back off again. So these are all the 40 watt bulb readings, of course. They're very accurate. 39.89 is quite a high deal of accuracy. But if we continue on, here we go. This is when it goes back to zeros. So as I mentioned in the demonstration, the energy does not reset. This is something that could be changed, but it doesn't really bother me. And so I have left it as is. But this is when I am swapping the bulbs. We can continue past all of these zeros here. We'll see it turns on again. Here's the moment where it's turning on and adjusting, and then here it is up to 120 volts. We see that the current has been measured out to 0.49 amps, and this equates to 58.64 watts, which is our 60 watt bulb. You'll see that it fluctuates very, very minutely, not very much, but the readings are essentially constant, which is what I was hoping for. So if we continue to scroll past the 60 watt bulb measurements, here we can see I've turned it off again. This is where I'm swapping to the final bulb, the 100 watt. And here we go, it is turned back on, and we see that we are reading 0.83 amps, just about 1 amp, which equates to 100.53 watts. This is our final bulb, and all of these values line up exactly as they did on the LCD, just as the measured values were in the demo. And then, once again, here I am adjusting the potentiometer on the final one, and I put it back up to the full brightness to see 100 watts again, and then we should see it turn off at the end, and then the file ends once I press the Safe Eject SD button. So this is a brief look into the SD card data that is written every time that an SD card is connected and a demo is performed. And as you can see, the values line up with what were displayed and of course thus what were measured. Alright, so after that demo, I just wanted to go ahead and do another little recap of this project in its entirety. So first of all, this project is a 120 volt AC load measurement device. It measures the voltage and current, and from these values calculates the power and energy of a given load, and it displays these on an LCD as well as an SD card, as we just witnessed from the demonstration. This project was created as a part of the ECE5000 Term 5 Electrical Engineering Design course. In this video, we went through the steps of development, and we talked about where it started versus where it ended up, and how I came along this path, and how the design is what it is today. If I were to suggest someone else to do this project, what are some things that I may consider to do differently, you may be asking? So firstly, I would consider creating a custom PCB. Now what does this mean? The Arduino Shield is nice and it was easy to use and easy to solder, but if I had more time, I would have designed my own custom PCB and perhaps included the ACS712 current sensor and the ZMPT101B voltage sensor on this PCB, and perhaps even the SD card module if I could make it work, just so that there's less going on and it is a much cleaner design, and you can even create your own PCB that attaches directly to the top of the Arduino Uno like a shield, but it is your own custom design. I think this would have been nice, and had I had the time and resources to do this, I of course would have done that, so that's one suggestion. A second suggestion is a much smaller housing. Mine is fine. There's tons of space inside. All the components are housed and secured nicely. But if I had the resources and the ability, I would have 3D printed a smaller housing that fits them just a little bit more snug. And then you can, of course, get the color customizations of a 3D housing. I would definitely recommend to anyone doing a project similar to this to use sensors as I did, as it's much safer to use components or ICs that are designed for this purpose, rather than attempt to transform and rectify an AC signal yourself, which can be dangerous or a little confusing to some. These sensors made it very easy and they weren't expensive by any means, so I would definitely recommend these to anyone who's doing a similar project with AC voltages. Alright, so there we go. This has been my ECE5000 electrical engineering design project. I, of course, am Noah Bailey, a Term 5 electrical engineering student at Memorial University. We just went through my entire project from start to finish and where it is today of my 120 volt AC load measurement device. All of the previous videos are on my YouTube page, and I will put some end cards at the end that you can click to go to the previous parts if you wanted to check those out. But all in all, thank you for watching, and I hope you enjoyed.